Good day. The research that I am about to present is about the corrosion inhibition efficacy of Mimosa pudica leaf extract on dental instruments. The researchers are Jona Juaneza, Helena Velasquez, Patricia Pamohino, Rency Dela Rama, Julleanne Fajardo, Dr. Shirley Wong, and yours truly. My name is Angel Urbano and I will be your presenter today. Demand for autoclave sterilization steers some of the critical items used in dental practice closer to their inevitable demise. Critical items are medical instruments that enter sterile tissue or the vascular system. They are at high risk for infection and are indicated for heat sterilization prior to usage to decontaminate them from microorganisms. In dentistry, these critical items include surgical instruments and dental scalers. Most of the surgical instruments used today are made of stainless steel. Surgical instruments are commonly identified as A1S1304 austenitic stainless steel and A1S1420 martensitic stainless steel. The Ufredi company uses dental instruments which, under the X-ray fluorescence analysis, is composed of the following chemical composition: weight percentage 72.1 iron, 0.19 carbon, 0.55 silicon, 1.75 manganese, 17.2 chromium, 0.45 molybdenum, 6.19 nickel, 0.05 vanadium, 0.04 niobium, 0.48 copper, 0.57 aluminum, 0.03 tungsten, 0.13 cobalt, less than 0.03 phosphorus, and less than 0.03 sulfur. This dental instrument is corrosion resistant austenitic steel. However, corrosion resistant is not the same as immunity to corrosion. Corrosion is the destruction of the surface of the metal due to its electrochemical reaction with its environment. Corrosion of surgical instruments has many causes. Chemically, corrosion is caused by halide ions, most commonly chlorides, that destroy the passive layers and cause pitting or stress corrosion in an instrument. Chlorides in fresh water, insufficient demineralized water used for the final rinse and steam sterilization, organic residues such as blood dried on the surface of the instrument, and laser marks can cause corrosion. Steam sterilization kills microorganisms and destroys their replication abilities. A moist heat sterilizer or autoclave uses steam at 121 to 134 degrees Celsius at a pressure of 15 psi within 15 to 30 minutes. However, autoclave sterilization can cause damage on polymers and corrosion on metallic instruments due to its moisture. Corrosion reduces the strength of the metal and makes them vulnerable to breakage. Corroded metal is full of anaerobians, and metal injuries have a high risk of infection rate. Corrosion inhibition is a process that can reduce, control, or prevent electrochemical reactions of a metal to its environment by forming a physical barrier over the metallic substrate. This can impede the corrosion reaction. An example of corrosion inhibitor used in controlling corrosion in closed environments is vapor phase corrosion inhibitor, or VCI. Metal absorbs VCI, whereby it forms a thin monomolecular barrier film of oxide layer. However, certain VCI formulations can be toxic. In fact, and nitrosoamine VCI are both carcinogenic and hemotoxic. Researches on plant-based corrosion inhibitors are getting a lot of attention. They are biodegradable and do not accommodate noxious complexes in heavy elements. Organic passivators can inhibit corrosion either by forming a barrier of oxides on the metal surface or using chemisorptions to counter metal ions that can cause corrosion. Parts of some plants, such as henna, Lawsonia inermis, carica papaya, date palm, and Nypa fruticans worm, are effective corrosion inhibitors for metals and alloys. Another example of a green corrosion inhibitor is Mimosa pudica. Mimosa pudica, or shame plant, or macaia, is a spiny subshrub considered to be an invasive pest in Asia and in the Pacific. It has compound leaves and small globular pink flowers. Its leaves contain phytochemicals that have electron-donating heteroatoms in their aromatic or long carbon chain. The phytochemicals present, such as saponins, tannins, flavonoids, phenols, quinones, and alkaloids, can enhance their electropositivity and lessen the chances of generating corrosion. This study would like to address the scarcity of readily available organic and non-toxic corrosion inhibitors for dental instruments. Statement of the problem. The researchers aim to assess the corrosion inhibitor properties of Mimosa pudica leaf extract on austenitic stainless steel dental instruments which underwent the autoclave sterilization process by weight loss analysis in order to identify potential ways to mitigate corrosion and extend the lifespan and performance of austenitic stainless steel dental materials. In order to answer the above cited problem, a specific answer to the following questions will be sought. What are the physical properties of the leaf extract of Mimosa pudica in terms of color, pH, and odor? What are the effects of autoclave sterilization on austenitic stainless steel dental instruments? How does Mimosa pudica leaf extract inhibit the corrosion of austenitic stainless steel dental instruments? What are the phytochemicals present in the leaf extract of Mimosa pudica that permits its corrosion inhibition properties? For the hypothesis, there is no significant efficacy of corrosion inhibition of Mimosa pudica on austenitic stainless steel dental materials. The researchers use an experimental approach in this study. The focus of this study is to test the corrosion inhibition efficacy of Mimosa pudica leaf extract during autoclave sterilization of austenitic stainless steel. Collection and preparation. Mimosa pudica. Sample species were collected from Pampanga, Philippines. The collected samples were authenticated and verified by the Bureau of Plant Industry in San Fernando, Pampanga, Philippines. The Mimosa pudica plant was separated among other weeds and then washed thoroughly under running tap water. 5 kilograms of Mimosa pudica plant will be shade dried for 4 weeks. Then the leaves will be separated and it will be pulverized using a pulverizer. The yield will be immersed in 95% ethanol for 3 days and then filtered with Wattmann filter paper. Dental instrument. This experimental research will use a brand new periosteal mold number 9 from Euphrates. It will be cut into 12 parts using a metal grinder. Each piece will be measured for their surface area. Physical property evaluation. Physical properties of the extract will be evaluated based on the pH, odor, and color. Phytochemical test. The ethanolic extract of Mimosa pudica was subjected to chemical screening for identification of active chemical constituents. Tests for tannins, saponins, flavonoids, alkaloids, sterols, phenols, quinones, and anthraquinones. Immersion. After testing for physical properties and phytochemicals, the leaf extract is placed in a rotary evaporator. Then, the extract will be distributed into 3 concentrations: 10% leaf extract with 90% distilled water, 50% leaf extract with 50% distilled water, and 90% leaf extract with 10% distilled water. 4 groups of dissection dental instruments with each having 3 subgroups will be used. 1 is for the control group and 3 is for the experimental group. The control group will not be soaked in the Mimosa pudica leaf extract solution, but it will undergo different autoclave cycles. On the other hand, the experimental group will be immersed in the 10%, 50%, and 90% leaf extract concentrations for 3 hours and will undergo different autoclave cycles. Before undergoing autoclave sterilization, both the control group and experimental group will be weighed in an analytical balance. Each group will undergo autoclave sterilization with each of the subgroups placed in a self-sealed sterilization pouch and then deposited in a metal sterilization box before being placed in the autoclave machine. Autoclave cycles. One metal coupon from the control group and one from each concentration will be placed together in 3 rounds of autoclave sterilization. The same will be done with 5 rounds and 7 rounds of autoclave sterilization. These autoclave cycles will be the corrosion environment. After the autoclave cycles, the metal coupons will be weighed again. Weight loss method and inhibition efficiency. Weight loss method, also known as gravimetric method, has been used by several studies to determine the corrosion rate of metals. It is a quantitative method used in measuring external or internal corrosion in metallic structures. It is the oldest, yet simplest method by measuring the difference in mass of the subject before and after it has been immersed in a corrosive medium for a specified amount of time. Despite its disadvantage of being time-consuming and unable to determine the mechanism of corrosion, it is still being used in recent studies regarding corrosion. The weight loss method is used to obtain data about the inhibition efficiency of a corrosion inhibitor by measuring the weight loss before and after the subject has been coated by a substance used as corrosion inhibition. Results and discussion. Physical properties of Mimosa pudica leaf extract reveal a dark green color indicative of chlorophyll presence and an accompanying grass-like odor suggesting the existence of organic compounds. The measured pH of 5.59 indicates a slightly acidic nature, offering insight into the extract stability and potential interactions. These properties collectively provide valuable information for applications in various industries, including cosmetics, perfumery, and pharmaceuticals, guiding researchers and product developers in understanding the chemical composition and suitability of Mimosa pudica leaf extract for specific purposes. What are the effects of autoclave sterilization on austenitic stainless steel dental instruments? Table 1. Weight of metal coupons in milligrams before autoclave sterilization and after autoclave sterilization. Table 1 presents the weight of metal coupons measured in milligrams before and after sterilization across different cycles and varying concentrations of sterilizing agents. Each row corresponds to a specific cycle, and columns are organized based on the control group and the 3 different concentrations. The values represent the weights of metal coupons before autoclave sterilization and after autoclave sterilization. For instance, in the first row, or cycle 3, the weights of the control group before and after sterilization are 2014.1 milligrams and 2010.9 milligrams respectively. Similarly, the corresponding weights for the 10%, 50%, and 90% concentrations are provided. This table is crucial for assessing the impact of autoclave sterilization on the weight of metal coupons under various conditions, providing valuable data for analyzing the effectiveness of sterilization processes across different cycles and concentrations. Researchers can use this information to draw conclusions about the stability and integrity of the metal coupons after undergoing autoclave sterilization under different conditions. Table 2. Surface area of each metal coupon. The Table 2 presents the surface area values in arbitrary units of metal coupons. subjected to different corrosion cycles, represented by control, 10%, 50%, and 90% exposure levels. The cycles are denoted as 3, 5, and 7. Analyzing the data reveals a dynamic pattern of surface area changes over the corrosion cycles for each exposure level. Notably, the control values consistently decrease, suggesting a progressive reduction in surface area. The 10% exposure level exhibits a fluctuating trend with an initial decline at cycle 3, followed by a substantial increase at cycle 5 and a subsequent decrease at cycle 7. In contrast, the 50% and 90% exposure levels demonstrate more erratic patterns, with values oscillating between significant increases and decreases across the cycles. This variability in surface area data underscores the complex interplay of corrosion processes, with differing impacts at distinct exposure levels and cycles. Further analysis and experimentation are essential to understand the underlying mechanisms influencing these surface area variations. Table 3. Weight loss method. Table 3 shows that as the number of cycles increases, weight loss decreases, indicating potential improvement in the corrosion inhibition effect over time. Additionally, a trend is observed where higher concentrations of Mimosa pudica leaf extract result in lower weight loss, particularly evident at 50% and 90% concentrations. Specific observations for cycle 3 indicate improvements with increasing concentrations, with the 50% concentration showing significant effectiveness. Similar trends are noted for cycle 5 and cycle 7. In conclusion, Mimosa pudica leaf extract demonstrates efficacy in inhibiting corrosion on dental instruments. The effectiveness is concentration dependent, with higher concentrations exhibiting better corrosion inhibition. Furthermore, longer exposure or more cycles enhances the corrosion inhibition effect. How does Mimosa pudica leaf extract inhibit the corrosion of austenitic stainless steel dental instruments? Table 4. Inhibition efficiency of Mimosa pudica in 10%, 50%, and 90% concentrations. Table 4 outlines the inhibition efficiency of Mimosa pudica at different concentrations, 10%, 50%, and 90%, in cycles 3, 5, and 7, with lower values indicating higher efficiency. The control group, representing no inhibition, exhibits efficiency values from 0.10013 to 0.158888 at 10% concentration. Efficiency decreases from cycle 3 to 7. The 50% concentration shows a notable increase from cycle 3 to 5, followed by a slight decrease in cycle 7. The 90% concentration maintains relatively stable efficiency. Analyzing concentrations, the 50% concentration surpasses others in cycle 5, while the 90% concentration demonstrates greater stability. Variability exists across concentrations and cycles, indicating complex interactions. In cycle comparison, the 50% concentration has the lowest efficiency in cycle 3, but the highest in cycle 5, and efficiencies tend to decrease for 10% and 50% concentrations in cycle 7. Implications include the potential effectiveness of the 50% concentration in inhibiting, requiring further investigation. The stability of the 90% concentration suggests a sustained inhibitory effect. Temporal dynamics are crucial, as seen in varying trends across cycles. Understanding biological significance necessitates additional context on the specific process being inhibited. What are the phytochemicals present in the leaf extract of Mimosa pudica that permits its corrosion inhibition properties? Table 5. Phytochemical constituents of Mimosa pudica leaf extract. The phytochemical analysis of Mimosa pudica leaf ethanolic extract reveals a diverse array of bioactive compounds, including tannins, saponins, flavonoids, alkaloids, sterols, phenols, and quinones. The presence of these constituents suggests potential health benefits such as antioxidant, anti-inflammatory, antimicrobial, and cardiovascular effects. Notably, the absence of alpha-quinones in the extract indicates a lack of compounds associated with certain laxative properties. While these findings imply therapeutic potential, further research is required to comprehensively understand and exploit the medicinal qualities of Mimosa pudica, underlining the importance of continued investigation into its phytochemical composition and potential pharmacological applications. Answer to hypothesis. There is no significant efficacy of corrosion inhibition with Mimosa pudica on austenitic stainless steel dental materials. The analysis of variance, ANOVA, with repeated measures was conducted to assess the corrosion inhibition efficacy of Mimosa pudica on austenitic stainless steel dental materials. The within subjects' effects were examined for both concentration level and the interaction between concentration level and autoclave cycles. For concentration level, the F statistic was 0.360 with a p-value of 0.788, suggesting no significant impact on corrosion inhibition. Similarly, the interaction effect of concentration level and autoclave cycles yielded an F statistic of 0.379 with a p-value of 0.777, indicating no significant combined influence. The residual within subject effects, representing unexplained variance, were relatively small. Moving to between subjects effects, the autoclave cycles factor showed a trend, as indicated by an F statistic of 12.7 with a p-value of 0.174. However, this trend did not reach statistical significance at the 5% alpha level. The residual between subjects effects represented unexplained variance between different autoclave cycles. In summary, the analysis does not provide sufficient evidence to reject the null hypothesis, suggesting no significant efficacy of corrosion inhibition of Mimosa pudica on austenitic stainless steel dental materials under the tested conditions. The concentration levels, interaction with autoclave cycles, and autoclave cycles alone did not exhibit statistically significant effects on corrosion inhibition. Conclusion. Corrosion of metals is inevitable over time. It is because of other factors such as exposure to moisture that hastens its process. The role of corrosion inhibitors is to prolong the passivation of the metal and keep corrosion at a minimum. Mimosa pudica leaf extract contains tannins, saponins, flavonoids, alkaloids, sterols, phenol, and quinones which adsorb to the surface of the metal and acts as a barrier. Using the weight loss method, it is observed that higher concentrations of Mimosa pudica leaf extract result in lower weight loss, particularly evident at 50% and 90% concentrations. The results in weight loss method demonstrated that the effectiveness is concentration dependent, with higher concentrations exhibiting better corrosion inhibition. It also stated that longer exposure enhances the corrosion inhibition effect. However, the inhibition efficacy of Mimosa pudica leaf extract showed that there is potential effectiveness of the 50% concentration, and the stability of the 90% concentration suggested a sustained inhibitory effect. However, using the analysis of variance, or ANOVA, with repeated measure to assess the corrosion inhibition efficacy of Mimosa pudica leaf extract on austenitic stainless steel dental instrument that underwent autoclave sterilization, statistics showed that the concentration level suggests no significant impact on corrosion inhibition, as well as the interaction effect of concentration level and autoclave cycles. The potential of Mimosa pudica leaf extract should be further explored in its corrosion inhibition and antibacterial properties. Corrosion of dental materials under autoclave sterilization should be investigated thoroughly. That concludes our presentation. Thank you and God bless.